In the silent darkness of the cosmos, among billions of galaxies and uncountable suns, there exists a delicate balance, a cosmic dance between creation and collapse. Every shining star we see in the night sky is a fragile victory against gravity's relentless pull. Stars live because of an exquisite equilibrium. Deep within their blazing cores, immense gravitational forces squeeze atoms so tightly that nuclei fuse, releasing torrents of energy. This outward radiation pushes back against gravity, holding the star in a delicate truce. It is a dance that can last billions of years, an enduring standoff between light and darkness, between the hunger of gravity and the radiance of fusion. Our own sun, for instance, has maintained this balance for nearly 5 billion years, quietly fusing hydrogen into helium, shining steadily upon the worlds that circle it. And one day, when its hydrogen fuel is gone, it will change, swelling into a red giant, then fading into a white dwarf, a tiny ember of its former glory. But not all stars go gently. In the vast arenas of space, there are stars that are titans, many times more massive than our sun. These giants live fast and die young. When their hydrogen is gone, they burn hotter, fusing heavier and heavier elements in a frantic effort to resist gravity's crushing grip. Inside such a star, a furious sequence unfolds. Carbon fuses into neon over centuries, neon to oxygen in a year, oxygen to silicon in months, and silicon to iron in a single day. Each stage shorter, more desperate, as the fuel runs thin. And then the process stops. Iron, the cosmic dead end. Iron cannot fuse to release energy, it is nuclear ash. The furnace falters, and gravity, long held at bay, finally wins. The core collapses. Imagine a star tens of times more massive than the sun, its heart imploding in a fraction of a second. The collapse is so violent that electrons and protons are forced together, merging into neutrons. The very matter that once powered light itself is now crushed into a form denser than the nucleus of an atom. What follows is one of the most awe-inspiring events in the universe, a supernova. The outer layers of the star, rushing inward at a quarter of the speed of light, rebound off the newly formed core, sending a shock wave roaring outward through space. For a brief moment, mere seconds, the dying star outshines entire galaxies. And in that violent instant, it seeds the universe with the heavy elements forged in its heart: gold, silver, uranium, and countless others, the raw ingredients of worlds yet to come. When the light fades and the fury subsides, what remains is no longer a star as we know it. It is smaller than a city, yet heavier than the sun. It no longer shines, but it glows, a smouldering ember of cosmic collapse. It is a neutron star, a relic of death, and a monument to the extremes of physics. In these tiny remnants, the universe expresses its most extraordinary form of matter. A teaspoon of it would weigh billions of tons, a mountain's worth of mass compressed into the size of a marble. To understand a neutron star is to peer into the very limit of what matter can endure before it surrenders to the pull of a black hole. And yet, they exist. Billions of them, the remnants of giants that once blazed across the sky. In the next part, we'll journey deeper into the heart of these stellar remnants. We'll peel back their layers, descend through their impossible crust, and discover what lies within the densest objects in the known universe: the neutron stars themselves. When the brilliant chaos of a supernova fades and the universe grows quiet again, what remains behind is unlike anything else in existence: a neutron star. These are not ordinary stars. They are the skeletal remains of titans, the compressed hearts of once mighty suns. Only about 20 kilometers across, yet so dense that a single teaspoon of their material would weigh more than a mountain range. Imagine holding Mount Everest in the palm of your hand, if such a thing were possible. It's almost impossible for the human mind to grasp. We have no real experience with such extremes. These objects defy our intuition. They bend the rules of matter itself. A star reborn in collapse. When the collapsing core of a massive star reaches its limit, the unimaginable happens. Gravity crushes protons and electrons together, forming neutrons. What was once a sea of ordinary atoms becomes a single, colossal nucleus, a sphere of nuclear matter packed tighter than any substance we can conceive. At that moment, something beautiful yet terrifying occurs. The collapse halts, balanced, just barely, by the strange rules of quantum mechanics. The neutrons, bound by the Pauli exclusion principle, refuse to be packed any closer. This neutron degeneracy pressure is all that stands between the star and total oblivion. If it were any denser, even this final resistance would fail, and the star would vanish into a black hole. But for now, it endures as a neutron star. A star reborn through destruction. A glimpse from the outside. From the outside, a neutron star appears deceptively simple, a small, incredibly dense sphere glowing faintly in X-rays. But appearances are deceiving. Its gravity is so strong that light bends around it, allowing us to see not just the front, but parts of the back as well. If you could somehow stand on its surface, though of course you couldn't, the pull of gravity would be unimaginable. You'd weigh 100 billion times more than you do on Earth. A single step would crush you instantly, atoms torn apart by sheer force. The surface itself blazes at over 1 million degrees Celsius compared to the sun's mere 6,000. It's a landscape of impossible extremes, both alien and eerily beautiful. Beneath the surface, the layers of a neutron star. Let's take a mental journey beneath that scorching crust, down into the very heart of this cosmic remnant. The outermost layer is composed of iron, the same element that formed at the end of the star's life. These iron atoms are squeezed together so tightly that their electrons float freely, forming a shimmering sea of conductivity, an ocean of charged particles. As we descend, the pressure rises dramatically. Atoms lose their individuality. Their nuclei are forced closer and closer until protons merge with electrons, turning into neutrons. The deeper we go, the fewer protons remain. And then something extraordinary happens. At a certain depth, the nuclei themselves begin to deform, stretched and crushed by unimaginable pressure. Protons and neutrons rearrange into bizarre, spaghetti-like shapes. Physicists call this nuclear pasta, and despite the whimsical name, it may be the strongest material in the universe. Sheets, tubes and blobs of nuclear matter, lasagna and spaghetti, that resist breaking even under forces billions of times stronger than anything on Earth. It is matter at its absolute limit. These tangled structures may even form tiny mountains on the neutron star's surface, mere centimeters high, yet more massive than entire mountain ranges back home. The mysterious core. And beneath this nuclear labyrinth lies the true mystery, the core of the neutron star. Here, matter is compressed beyond the comprehension of physics as we currently know it. The density becomes so great that neutrons themselves might dissolve, releasing their constituent quarks into a swirling sea known as quark-gluon plasma. Some theories suggest that strange quarks, a heavier cousin of the up and down quarks that make up ordinary matter, could emerge, transforming the core into something exotic, strange matter. If true, a single drop of this strange matter could, in theory, convert everything it touches into more of itself. A runaway transformation of normal matter into something utterly alien. We don't know for sure. These are frontiers at the very edge of human understanding. To truly know what lies at a neutron star's heart would require physics that does not yet exist. The spinning remnants of giants. Now imagine what happens when these objects spin. When the massive star collapsed, it conserved its angular momentum, the same way an ice skater spins faster when pulling in their arms. As a result, the newly born neutron star can rotate hundreds of times per second. A city-sized object spinning faster than a blender under pressures that defy reality. It's staggering. This rapid spin, combined with the star's intense magnetic field, creates beams of electromagnetic radiation that sweep through space like cosmic lighthouses. Each time the beam crosses our line of sight, we detect a pulse, and so we call them pulsars. They blink with perfect regularity, marking the passage of time across the cosmos more accurately than atomic clocks. For decades, astronomers used these signals to map the universe, navigate spacecraft, and test the very fabric of general relativity. Their magnetic fields are the strongest known in the universe, a quadrillion times stronger than Earth's. In their youth, these hypermagnetized stars are called magnetars, and their energy bursts can disrupt electronics and distort space itself, even from light years away. These are not dead stars. They are living relics, engines of radiation spinning silently in the darkness, whispering across the void. It's humbling to think that these tiny remnants, so easy to overlook in the cosmic expanse, are among the most powerful and mysterious objects ever known. They are the ghosts of stars, yet in their silence they speak volumes about the laws that shape our universe. And as extreme as they are, their story is not yet over. Because sometimes neutron stars find each other, drawn together by gravity's eternal pull. And when they do, something even more spectacular unfolds. In the next and final part, we'll witness the ultimate fate of these cosmic remnants. The dance of death between neutron stars, the creation of heavy elements, and the story of how the ashes of dying suns became the building blocks of life and of us. In the vast quiet of the cosmos, two neutron stars orbit one another, remnants of once great suns locked in a slow, spiraling dance. Each revolution brings them closer together. Each passing moment they lose a tiny bit of energy, radiated away as gravitational waves, ripples in the very fabric of space-time. Over millions, sometimes billions of years, their orbit decays. They circle faster, closer, tighter, until at last, the inevitable happens. The dance of death when neutron stars collide. Imagine it, two objects, each more massive than our sun but no larger than a city, hurtling toward each other at a significant fraction of the speed of light. Their immense gravitational fields twist space-time itself into a swirling storm. As they merge, the universe shudders. The collision is so violent, so cataclysmic, that for a brief instant it releases more energy than all the stars in the observable universe combined. We call this event a kilonova, a cosmic explosion unlike any other. Unlike a supernova, where fusion ceases, a kilonova is born from destruction itself. The neutron-rich matter flung out in the collision tears apart and reassembles, creating new atomic nuclei. It is here, in this fleeting moment of chaos, that the heaviest elements in the universe are forged: gold, platinum, uranium, rare earth metals. The atoms that will one day glint in jewelry, power our technology, or lie deep within the crusts of planets. Every ring, every circuit, every spark of metal that shapes our civilization, all of it was created in a cosmic collision between two dead stars. When we look at gold, we are looking at the aftermath of a kilonova, a fragment of a star's death that has traveled across billions of years to become part of our world. The birth of a black hole. After the explosion fades, the two neutron stars, now fused, may cross a final threshold, collapsing under their combined mass into a black hole. The cycle begins again, a new singularity born from the ashes of the old. It's poetic, in a way. Stars must die, not once, but twice, to create the universe as we know it. First in a supernova to leave behind a neutron star, then again in a kilonova to forge the elements that build worlds. And when their remains finally fall into darkness, the story doesn't end, because those elements, scattered across the cosmos, will someday be gathered again by gravity's patient hand. Clouds of dust and metal will swirl together, forming new stars, new planets, and perhaps new life. From stardust to sentience, our own solar system was born this way, out of the remnants of countless ancient stars. Every atom in your body once resided in the heart of a sun, the calcium in your bones, the iron in your blood, the gold in your ring. All of it forged in the crucibles of stellar death. We are, quite literally, the children of Neutron Star, the descendants of their final magnificent acts of destruction. When we look up at the night sky, we're not just observing distant suns, we're seeing the very history of our own existence written in light. Each twinkling point a reminder of the stars that came before, and the unbroken chain of creation that led from their fire to our consciousness. The universe within and without. There's a certain humility in realizing how small we are, and yet how connected we remain to the grandest forces in existence. The same laws that govern the heart of a neutron star also shape the neurons firing in your brain as you ponder it. The same cosmic pressures that crush atoms into neutrons once built the materials that make up your hands. To study the universe is to study ourselves. To gaze at a neutron star is to look back at the origin of everything we are. Neutron stars are the universe's storytellers. They remind us that endings are never truly ends, only transformations. From the ashes of collapse come new beginnings, new worlds, and perhaps new eyes to wonder at the night sky. Every bit of progress, every thought, every dream of humanity is in some distant sense an echo of those long-dead stars. Their energy, their atoms, their story carried forward through time until it became us. And maybe one day, far in the future, when our own sun has burned its last, some distant civilization will look toward the remnants of our system and wonder what kind of beings once lived here, what they built from the dust of neutron stars. In the end, the story of neutron stars isn't just about death or collapse. It's about resilience, transformation, and the eternal cycle of creation that binds every corner of the universe together. We are not separate from the cosmos. We are the cosmos, made aware of itself. And that, in the quiet vastness of space, is the most extraordinary thing of all.